function little phi of y, right? Because they're bound together, little phi and big phi. Okay. So rather than try and just derive this from scratch, right? Let me go ahead and give you the answer as a theorem, and we'll see why it worked. Okay. So let's say that U is C2 and it solves the Poisson equation. Then the following thing is true. So U is equal to this integral over G and F. Okay. And then we have this correction, which is actually going to be the normal derivative xy gy that's taken over the boundary, right? dsy here. Okay. All right. So this gives us what we want, right? But I still don't necessarily maybe know what this little phi of y is, right? So to get this little phi of y, okay, we'll talk about that. I think if we have time today, we use what's called the method of images for a lot of different situations, okay? Otherwise, we can usually solve it using eigenfunction expansions, something like that, okay? But this correction term here, right, this w of x, it turns out that is also made up of the Green's function itself, right? It's a normal derivative of the Green's function around the boundary and integrated against the boundary term there. Okay. So to prove that this works, right, we can see that the first integral clearly solves the homogeneous boundary value problem, right? Minus Laplacian of u equals f, u equals 0 on the boundary, okay? And this is essentially since minus Laplacian of g f is equal to delta f, which is equal to f, right? And then gf is equal to 0 at x is in delta u, okay? Essentially by construction, right? Because we wanted that the boundary term here, right, it should vanish, right? So we'll just have a 0 times f, okay? So we'll satisfy our boundary condition there, okay? What about the second integral? The second integral is the one that we have to work on. But this is the correction term that we get to account for our inhomogeneous boundary, okay? Well, it's harmonic, okay? Since g of xy is harmonic, okay? And that's in x lives in u, then for any y on the boundary, right? Because that's what we're integrating over. And g is only modified by differentiating and integrating, okay? Which are both linear operations, right? So to show that it satisfies the boundary condition, what do we need to do? We need to demonstrate essentially that minus dg dny goes to a delta function, delta distribution, as x goes to the boundary, okay? How do you think we'll do this? Stop and think about it. What are our main tools, especially for dealing with integrals around boundaries, okay? You'd be thinking Green's identities, or maybe the divergence theorem. Okay, so we'll use the divergence theorem in order to solve this, right? Strikes again. So to deal with the singularity in our Green's function, g of x, y, at y is equal to x, what do you think we're going to do? We're going to do what we've done before in these types of situations. We're going to cut out a ball of size epsilon around this singularity, okay? And so for any u, let's see, 2 on the closure, right, then the following thing is true. The integral over v epsilon of uy, the Laplacian of phi of xy minus phi of x, y, Laplacian u, y, dy, okay, is equal to the integral dv epsilon of uy d phi of xy divided by dny minus phi xy du y dny, okay, dsy. So this is using the divergence theorem, right, on each of those terms. And we get a nice cancellation. So what else do we know? Well, we know that phi is going to be harmonic so long as y is not equal to x, right? Because the Laplacian of phi, right, is equal to 0 everywhere except where y is equal to x, and that's, where you have this delta distribution singularity, okay? So that's why we, cut out the ball. So that means the first term on the left-hand side is 0. Okay, so we're starting to get rid of some terms. Now the boundary, it has 2 parts, right? What 2 parts does the boundary have? Well, first of all, it has du, and second of all, it has the boundary of the ball that we cut out of u, okay? And we will show that the contributions from the ball, dbx epsilon, go to 0 as epsilon goes to 0, okay? So we can zero out more terms there. So in order to do this, let's compute a couple of these pieces of the integral, right? So the first of these is going to be this part, right? Evaluated on the surface of the ball. Okay, so let's let I epsilon equal the integral over the surface of the ball, u, y, d phi, dny, xy, dsy, okay? Well, if I take the limit as this goes to 0, right? As epsilon goes to 0, this is just going to become the average value of u, okay? So this essentially is going to behave like an average, okay, as in the Poisson equation proof, right? So if you go back to the proof that we did for the solution to the Poisson equation, okay, you find that we can show that essentially as we shrink this down, right, it's like you're averaging around the perimeter, okay, of to get the average of u, okay. Now let's do another piece of that integral now. If I let j epsilon equal the integral over the surface dB epsilon, okay, phi of x, y, du, dny, then we get that this is going to scale like what? Well, basically as we take epsilon to 0, okay, what do we know about this? Well, that this is going to start, it's going to be this quantity here, right, is going to be epsilon, this term here, right, is going to be epsilon. It's going to involve an epsilon to the n minus 1, right? Whereas this is a 1 over epsilon to the n minus 2, okay? So when n is greater than or equal to 3, right, this whole thing is going to scale like epsilon. Then when you have the logarithmic solution for n equals 2, this part is going to scale like log, and then you'll have you're going to have a term of order epsilon out in front, okay? So what we find then is that these are going to scale like epsilon log epsilon for n equals 2, and epsilon for n greater than or equal to 3. And that's going to go to 0 as epsilon goes to 0, okay? So the point is that that part is also is going to vanish, okay? So as epsilon goes to 0, we can say the following things, okay? First of all, minus the integral over the domain of our fundamental solution integrated against the Laplacian of u is going to be equal to all these different pieces, right? So u of x plus now the integral over the boundary of u, y, e phi, e n, y, x, y, minus phi of x, y, d u, d n, y, e s, y, okay? So, so this integral here, right, if we take the limit as epsilon goes to 0, it just becomes the integral over u, right? And now this part is vanished, okay? This part here is vanishing for the boundary with the ball, right? And we're just left with the boundary of u, okay? And then also this part u of x that we computed for that first interval, okay? Now, using that symmetry, of our solution, right? So take phi xy equal to big phi of xy, okay? Well, then phi of xy has no singularity, okay, at x equal to y, okay? And if we go through the calculation again with little phi xy, we get that I epsilon goes to 0, okay? Because we have no singularity for our little phi of y. So minus the integral of phi xy Laplacian of uy is going to be equal to the integral of du uy d phi x dny y minus phi of xy d u dny of y dsy, okay? I'll call this one here 2, right? Remember this one up here I'm calling 1, okay? And if we subtract 2 from 1, what we get is minus the integral over u of g xy Laplacian of u y dy equals u of x plus the integral over du u y dg dny xy dsy, okay? And so if we rearrange this, right, then we get our formula, okay, that we had before, okay? And so when minus Laplacian u equals f, right, on u, okay, and u is equal to g on du, then we have that u of x is equal to the integral gxy f of y dy minus the integral du dg dny xy g of y dsy. Okay, so that's what we wanted to prove today. Okay, so what did we do? Well, we used properties of the fundamental solution. Okay, we cut away the singularity, and then we shrank down that cutaway singularity, and we showed that we could use the divergence theorem to write the integral over the volume in terms of this difference of integrals over the surface of the domain, and zeroed out, and the epsilon goes to 0 limit in order to get this solution. So this is a solution to the Poisson equation, when you have an inhomogeneous Dirichlet boundary condition, you can extend this to the case of Neumann boundary conditions. We'll probably get to that, I think, next week. Okay, so I think I have maybe about 17 minutes left of time. Let me circle back to how we get these